Welcome to this puzzle guide. We'll be looking at the pigeonhole principle, which is a very simple statement but very powerful. Let me first discuss an informal version of it, which is in fact the reason why it is called the pigeonhole principle. So what we have is we have 3 cages and let's say 4 pigeons. So I have just denoted the pigeons by dots. And what we want to do is we want to put these 4 pigeons into these 3 cages. So the pigeonhole principle says that you will need to put at least 2 pigeons in one cage, meaning there will be a cage which will have to accommodate at least 2 pigeons. So of course we see this is very clear, but to illustrate, suppose I put this pigeon there and I don't want to accommodate, I don't want to have any cage in which there are more than 1 pigeon, then I'll have to put another pigeon there and then another pigeon there. But then where will this one go? This will have to go to either this or that, but then anywhere I'll put it, I'll have 2 pigeons in one cage. So it's not very illuminating. It's nothing out of the ordinary that this principle is saying. More generally, if you have what did I do? More generally, suppose you have P pigeons and they are to be put in C cages. So P pigeons and C cages. And suppose that number of pigeons is greater than the number of cages. Then what you can do is, what you can say is that some cage must accommodate at least 2 pigeons. This is exactly a generalization of what we said earlier. In our case, P were equal to, in the diagram above, P is 4, the number of pigeons is 4 and number of cages is 3. Alright, so this was an imprecise, not imprecise, but an informal statement. What is informal about it is cages and pigeons, because cages and pigeons are not mathematical objects. So to be very nitpicky, I would like to get into a formal description of the same. So suppose you have 2 finite sets x and y, and suppose we have a function from x to y, just any function. Then the pigeonhole principle says that if the cardinality of the domain is greater than the cardinality of the target of f, then f cannot be injective. What this means is f is not injective is same as saying that there exist x1 and x2 in x such that x1 is not equal to x2 and fx1 equals fx2. So there are 2 different points in the domain which are mapped to the same point in the target under f. So that's what it means for f to be not injective, and this is exactly the above, what we said earlier in the previous slide. What we did was just think of x as pigeons. These are our pigeons. These are cages. And f is an assignment of a pigeon to a cage. So if there are more pigeons and less cages, then some 2 different pigeons have to be assigned to the same cage. That's all. That's what this is. I mean, that's the formal, proper mathematical statement of the pigeonhole principle. Now, one can immediately make it more general. And let me state the generalization. I will not prove it because one can easily prove it oneself. But it's important that I state it. So suppose you have again finite sets, and let's say the size of x is m and the size of y is n, and assume m and n are greater than or equal to 1, meaning that we are not having empty sets here. So neither x nor y is empty. So each of them has at least one element. Okay, and then again we have a function from x to y. So then there is some point little y in capital Y such that this is the case, and I have to explain these notations. So this thing is nothing but those points in x which map to y under f. So this is not to suggest that f is invertible or any such thing. This is just a notation to take the pre-image of y under f. That's how we read it. And this is what it is. All those points in the set X which map to Y under F. Alright. And what is that guy? So this is a notation to mean. So let me explain this in a somewhat more general. So for a real number X, we write this ceiling X. This is read as ceiling X to mean the smallest integer which is greater than or equal to X. So just like in high school, we read the greatest integer function, which is the greatest integer less than or equal to X. This is the ceiling function, which is the smallest integer greater than or equal to X. So for example, the ceiling function of 2.5, let's say 2.5 is 3, because what are the integers which are greater than or equal to 2.5? They are 3, 4, 5, etc. And which one is the smallest among them? 3. So that's it. What about the ceiling of 2? That is 2. Because the integers which are greater than or equal to 2 are 2, 3, 4, 5, etc. And the smallest one among them is 2. So a very simple concept. And let us instantiate what this is saying. We can understand by instantiating this particular statement for various values. So let's say we just have, for m greater than equal to, for m greater than n, meaning you have kind of more pigeons than cages, then what is m by n ceiling? M by n ceiling is ceiling of something strictly greater than 1. And ceiling of something strictly greater than 1 is at least 2. So the statement says that there is some y such that the pre-image of y has size at least 2, meaning there are at least 2 things which map to the same thing under F, which is to say that F is not injective. So this is capturing the previous statement where we just said this much. So that much is contained here because we just showed it. And in fact, now to get a feeling for what more this is saying, suppose we had instead of 4 pigeons, we had, let's say, let me copy or translate these. Oops. Yeah. So suppose we had many of these. So we have 3 cages and 6. Let me get one more. Yeah. So suppose we have 7 pigeons and 3 cages. Then I would like to say that you will have a cage which will be accommodating at least 3 pigeons. So what we do is, okay, we put this guy there, then that guy there, and that guy there. And now we are forced to at least have one cage which will have 2, but then, okay, fine. We move those that way. And now there has to be a cage which will accommodate at least 3 pigeons. So if you just check, we had 7 pigeons and 3 cages, and the ceiling is exactly 3. So that's the kind of thing that is happening. You just write 7 as 3 into 2 plus 1. And this will show you that you'll have to have a cage which has more than 2 pigeons, and more than 2 meaning just 1 plus 1 extra. So therefore you get 3. And that is the statement of this thing. And I encourage you to mull over this if this is not immediately clear, but this is not saying anything very much more complicated than that. So this is the most general version of pigeonhole principle that I will be stating. And now let us look at some examples, some very simple examples. In this lecture, we will not be looking at very complicated examples. I'm making this lecture so that whenever we invoke the pigeonhole principle, I can just refer to this one so that the listener has some primer which he can use, he or she can use. So with that, let me give the first very simple example. So we have 8 integers, and we want to show that there exist I and j which are different, with the property that the difference of the integers corresponding to I and j, meaning ai and aj, is divisible by 7. So amongst these 8 integers, and there may be repetitions here, I'm not insisting that these are different integers or any such thing, there could be repetitions here. So we want to show that some 2 of these folks have the property that if you take the difference, then the difference is divisible by 7. And here is, before we apply the pigeonhole principle and see, in fact, how at all we are using the pigeonhole principle, let me just state a very simple fact, is that ai minus aj is divisible by 7, or not ai minus aj, let me write a minus or x minus y is divisible by 7, or let me just write n divisible by n, where x is an integer, y an integer, and n is some, let's say, natural number, if and only if x and y leave the same remainder when divided by n. So this is just a small note which we will use. So now let us use pigeonhole principle to solve this problem. I'll be very, very formal. So let x equals 1 to 8 and y equals 0 to 6, and you will see why I'm defining y that way. So define a map f which takes I to the remainder ai leaves when divided by 7. So what is the set y? The set y is just the set of all possible remainders that an integer can leave when you divide it by 7. So that's what y is. X is basically the collection of all the indices that you see here, and we are just sending the ith index to the remainder that ai leaves when you divide it by 7. And now by pigeonhole principle, since x has more elements than y, some 2 different elements in x will be mapped to the same element in y. So, which means that there are different I and j such that ai and aj leave the same remainder when divided by 7. And therefore, by this comment, we see that ai minus aj is divisible by 7. So that's it. And of course, you can generalize this. There's nothing special about 8 or 7 or anything. You can just put any n here, and then this would be n minus 1. That works, but fine. I mean, just for concreteness, I just took the example of 8. So it's a very, very simple example of an application of pigeonhole principle. Let us discuss a classical example and then we end this lecture. So this is very popular in any combinatorics graph theory book. You'll find this. What this says is the following. So you have 6 people. Then just with this much hypothesis, we claim that amongst these 6 people, you can find 3 people which are either pairwise mutually friends or pairwise mutually strangers. So I need to explain that. So first of all, we assume that given any two people, either they are friends or they are strangers. So there could be some weird relationships, like you could have a celebrity amongst the 6 people, then it's not clear if they are friends or strangers. But just assume that given any two people, either they are friends or they are strangers. Okay, so now what we are saying is that if you have 6 people, then you can find some 3 people in there, in that group, such that either these 2 will be strangers, these 2 will be strangers, and these 2 will be strangers. Or you can find 3 people such that these 2 are friends, these 2 are friends, and these 2 are friends. So it's an or, it's not and. Logical or. And it's not clear why such a thing should happen. Although this is a finite situation, so one can just list out all the possible scenarios and figure it out. But let us give a very nice argument using pigeonhole principle. So what we'll do is we will picture the 6 people as dots. So we have, for each person we will make a dot. So these are our 6 people. And now just let us fix one guy. So let me in fact maybe put a cross or something. Let me put a cross here. So let me just focus attention on this guy. And now this has 5 other people that it interacts with. So what we'll do is, if 2 people are friends, then we will join a blue edge between them. So if this guy and that guy were friends, then we'll join a blue edge between them. And if let's say 2 people were not friends, meaning they were strangers, let's say if this guy and that guy were strangers, then we'll just join a red edge between them. So this is how we will record the relationships, just by coloring the edges between any 2 people. The color of the edge records the kind of relationship they have, either they are friends or strangers. Okay, fine. So let us focus our attention on one person and what are the possible relationships he has with the other 5. So now this guy is emanating a total of 5 edges because there are 5 other people, and each edge is either red or blue because each one is either a stranger or a friend. Now since there are 5 people and only 2 colors, meaning there are 5 edges and only 2 colors, there must be a color that will be used in at least 3 edges. So think of it as 5 pigeons. 1, 2, 3, 4, 5. 5 pigeons. And the colors are cages. So you have a red cage and a blue cage. And each edge is kind of sent to one of the cages. So there must be a cage, meaning there must be a color where you are sending these many edges, which is 3. So there are 3 edges which get the same color. And without loss of generality, let us say that color is red. It could be blue also, and the same argument will go for that, but let us say that color is red. So let us say these 3 things are red. I mean, I'm just drawing some 3 red edges. It doesn't really matter what the order of that is because you can always shuffle these people around. So let's say these 3 are red edges. Now if this edge were also red, then we would have a red triangle, and that would mean that these 3 people have the property that they are mutually strangers pairwise. So if this is red, then we have a red triangle. If this is red, then we have a red triangle. And similarly, if this is red, then we have a red triangle. So in either of these 3 cases, we will be done. So the adverse case is that this edge is blue, this edge is also blue, and this edge is also blue, because in any other case we are done. But now we are forced to have a blue triangle. So, no matter what we do, what we see is that there must be a monochromatic triangle in it, meaning a triangle whose all three edges have the same color. And that is precisely what it means to have three people which are mutually friends or strangers. Because that's how the colors were capturing the relationships. So this is a very, very famous example of the application of pigeonhole principle. And I hope you enjoyed this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.